Hello, and welcome to Boring History for Sleep. Tonight, we turn our attention to the quiet, unassuming objects that form the very bones of our built world. Consider for a moment the humble concrete block. You have seen thousands, perhaps millions of them in your lifetime, forming the foundations of homes, the walls of schools, and the vast, windowless expanses of warehouses. They are so common, so utterly ubiquitous, that they fade into the background of our lives, seemingly as natural and undesigned as stone from a quarry. But if you were to measure one of these blocks, you would find a small, curious discrepancy. A block known throughout the industry as an 8 by 8 by 16-inch unit is, in fact, only 7 5/8 inches tall, 7 5/8 inches deep, and 15 5/8 inches long. This missing 3/8 of an inch on each face is not a manufacturing defect, nor is it an accident. It is the quiet, carefully calculated result of a 6-decade-long struggle for order in a world of industrial chaos. To truly understand the profound importance of this seemingly minor detail, we must travel back to a time when a concrete block was anything a maker wanted it to be, and examine the meticulous, painstaking process that gave us the standardized world we now take for granted. Our story begins in the early years of the 20th century, a period of tremendous industrial growth and urban expansion in the United States. The era of cast iron and heavy timber framing was giving way to steel and reinforced concrete, but for smaller structures, for foundations, and for the vast unmet need for affordable housing and commercial buildings, a new material was gaining prominence: the concrete block. The concept was not entirely new. Variations of artificial stone had been experimented with throughout the 19th century, but it was the invention of practical, hand-operated block-making machines, most notably the one patented by Harman S. Palmer in 1900, that truly democratized its production. Palmer's machine allowed a small crew of men to mix concrete and press it into molds, creating hollow-core blocks that were lighter, cheaper, and offered better insulation than solid stone or brick. This invention sparked a cottage industry. Across the country, small entrepreneurs, local builders, and even farmers bought these machines and went into business. The barrier to entry was remarkably low. One needed little more than the machine, a supply of cement, and access to a local aggregate, be it sand, gravel, crushed stone, or even industrial waste products like cinders from coal-fired furnaces, which gave rise to the colloquial term cinder block. This decentralized, localized production model was both a blessing and a curse. It made building materials widely available and affordable, fueling a construction boom, but it also created a state of near-total anarchy in terms of quality and dimensions. Imagine being an architect or a builder in, say, 1915. You might specify a wall to be built of concrete blocks. The blocks delivered to your job site from a supplier in one town might be 8 inches tall and 16 inches long. A supplemental order from a supplier in a neighboring town might arrive with blocks that are 8¼ inches tall and 15½ inches long. Another batch might be made with a different mold, producing a different texture, a different core configuration, and, most critically, a different compressive strength. Masons would struggle to lay courses that were level and true. Walls would have inconsistent appearances and, more alarmingly, unpredictable structural properties. An engineer could not reliably calculate the load-bearing capacity of a wall when the units themselves were of unknown and variable strength. The very promise of the concrete block, its efficiency and economy, was being undermined by its own lack of uniformity. This chaotic environment was the fertile ground from which the movement for standardization grew. The initial push came not from government regulators, but from within the industry itself, led by two nascent but influential organizations. The first was the Portland Cement Association, or PCA. Founded in 1916, the PCA's primary mission was to promote the use of Portland cement, the key binding ingredient in concrete. They quickly realized that the poor quality and inconsistency of many concrete products, including blocks, were giving the material a bad reputation. To promote their product, they needed to ensure it was being used correctly, and to create a baseline of quality, the PCA began publishing pamphlets, conducting research, and offering guidance to block manufacturers on proper mix designs, curing methods, and best practices. The second, and ultimately more critical, organization was the American Society for Testing and Materials, known then as ASTM. Formed in 1898, ASTM was a scientific and technical organization dedicated to the development of voluntary consensus standards. Its process was deliberately slow, methodical, and inclusive. It created technical committees composed of a balanced mix of producers, the block manufacturers, users, architects, engineers, and contractors, and general interest parties, academics, researchers, and government agencies. This structure ensured that no single group could dominate the standard-setting process, and that the resulting documents were based on sound science and practical application. In 1920, recognizing the growing need for order, ASTM chartered a new committee, Committee C10 on hollow building tile. While its initial focus was on clay tile, its scope soon expanded to include the burgeoning concrete block industry. The early work of this committee, and others that would follow, was foundational. They did not simply sit in a room and agree on a set of numbers. They had to first answer a series of fundamental questions. What are the essential properties of a concrete block that determine its performance? How can these properties be measured reliably and repeatably? And what are the minimum acceptable values for these properties to ensure safety and durability? The first and most important property they tackled was compressive strength. This is the measure of a block's ability to resist a crushing load, a critical factor for any material used in a load-bearing wall. To standardize this, the committee had to define a precise testing protocol. How large a sample should be tested? Should it be a whole block, or a coupon cut from the block? How should the block be prepared for testing to ensure its top and bottom surfaces were perfectly flat and parallel, so the load from the testing machine would be applied evenly? They experimented with grinding the surfaces, but this was time-consuming. They eventually settled on a process called capping, where a thin layer of a specialized material, like a sulfur-based compound or high-strength gypsum plaster, was applied to the bearing surfaces to create a smooth, level plane. Then there was the test itself. The capped block would be placed in a large hydraulic press. The machine would apply a load at a controlled, steady rate until the block fractured. The maximum load achieved before failure, divided by the gross cross-sectional area of the block, would yield its compressive strength, expressed in pounds per square inch, or PSI. The early ASTM specifications, developed through the 1920s, began to set minimum requirements. For example, a tentative standard might require an average compressive strength of not less than 700 psi for load-bearing blocks. This was a monumental step. For the first time, an architect could specify concrete block meeting ASTM specification CXX and have a reasonable assurance of the material's structural capacity, regardless of who manufactured it. The second critical property addressed was water absorption. A block that absorbs too much water can be problematic. It can lead to moisture wicking through a wall, causing dampness and damage. More critically, in colder climates, water absorbed into the pores of the concrete can freeze and expand, a process known as freeze-thaw cycling. This expansion can cause the surface of the block to spall and flake, and over many cycles, can lead to the complete disintegration of the unit. To standardize this, a testing protocol was developed. A block would be dried in an oven to a constant weight, then submerged in water for 24 hours. It would then be weighed again. The amount of water absorbed, expressed as a percentage of the block's dry weight, was its absorption rate. The early standards began to set maximum limits on absorption, particularly for blocks intended for exterior use, or for foundation walls exposed to soil and moisture. While these efforts on material properties were progressing, the thornier issue of dimensional standardization was also being debated. This was far more contentious. A block manufacturer had a significant capital investment in their steel molds. To tell a producer that their 8.25 by 16.5-inch block was no longer acceptable, and that they needed to buy all new 8 by 16-inch molds, was a major economic imposition. Resistance from the many small, independent producers was fierce. The PCA and other industry leaders argued that the long-term benefits of modular coordination, where all building components fit together in a predictable grid-like fashion, would far outweigh the short-term costs. The 1920s saw the beginning of this debate, with various nominal sizes being proposed. The most common contender was the 8-inch by 16-inch face dimension, with a standard height of 8 inches. This was appealing because it coordinated well with traditional brick masonry. A standard brick is roughly 2 2/3 inches high, so 3 courses of brick, with their mortar joints, would equal the height of one 8-inch high block. This allowed masons to easily combine the two materials in a single wall, a common practice. However, adoption was slow and voluntary. Throughout the Roaring Twenties, a builder on any given job site was still likely to encounter a frustrating variety of block sizes. The framework for order was being built, but the house was not yet in order. The arrival of the Great Depression in the 1930s had a complex effect on this process. On one hand, the collapse of private construction slowed the industry dramatically. Many smaller, less efficient block producers went out of business. On the other hand, the massive public works projects initiated by the federal government, such as those under the Works Progress Administration, became a powerful driver of standardization. Government contracts for post offices, schools, and infrastructure projects were often vast, and the agencies overseeing them demanded efficiency, quality control, and predictability. They began to heavily reference, and in some cases mandate, the use of materials conforming to ASTM standards. This federal purchasing power provided a significant incentive for manufacturers to modernize their equipment and adhere to the nascent national standards for both quality and dimension. During this decade, the technical committees at ASTM continued their slow, deliberate work. Tentative standards were revised and reissued, gradually becoming more refined and more widely accepted. One of the key documents to emerge and evolve during this period was the standard that would eventually become known as ASTM C90, the standard specification for load-bearing concrete masonry units. This single document would become the Bible of the industry. Within ASTM C90 and its predecessors, a crucial distinction began to be codified: the difference between various grades of block. It was recognized that a block used for an interior, non-load-bearing partition wall did not need to be as strong or as water-resistant as a block used for a foundation wall supporting a multi-story building. This led to the establishment of different classifications. For instance, a Grade A block might be defined as suitable for use in exterior walls below grade and for unprotected exterior walls above grade, requiring a higher compressive strength, perhaps 1000 psi, and lower water absorption. A Grade B block might be suitable only for protected use, such as an interior wall or an exterior wall that would be covered with a weather-resistant veneer, allowing for a lower compressive strength, perhaps 700 psi, and a higher absorption limit. This allowed for more economical construction, as builders could use the less expensive Grade B units, where the higher performance of Grade A was not required. This process of classification required even more meticulous testing and research. Committees had to study the effects of weathering on blocks of different densities and absorption rates. They had to determine the minimum compressive strengths needed to safely support typical construction loads, incorporating factors of safety to account for variations in materials and workmanship. This was not glamorous work. It involved years of casting concrete cylinders, crushing blocks in laboratories, and exposing wall panels to artificial weather chambers, all to generate the data needed to justify the numbers written into the standards. The 1940s, and the entry of the United States into World War II, proved to be the single greatest catalyst for the final push toward comprehensive standardization. The war effort required an unprecedented amount of construction to be completed in an incredibly short period of time. Military bases, munitions factories, and housing for war workers had to be erected almost overnight. Materials like steel and lumber were in critical demand for ships, planes, and armaments, making them scarce for construction. The concrete block, which used plentiful local aggregates and relatively little cement, became a material of strategic importance. The War Production Board and other government agencies took direct control of the national economy, and they had no patience for the inefficiencies of non-standard products. Logistics was paramount. An order for 500,000 8-inch stretcher blocks needed to be filled by multiple producers from different parts of the country, and every single block needed to be interchangeable. This top-down pressure effectively ended the debate over dimensions. The industry rapidly consolidated around a set of standard modular sizes. It was during this period that the concept of nominal versus actual dimensions became firmly entrenched. This was the elegant solution to the problem of the mortar joint. If you have an actual 8 by 16-inch block and you add a 3/8-inch mortar joint around it, the final unit in the wall is 8 3/8 inches by 16 3/8 inches. This creates a mathematical nightmare for designers and masons. The solution was to subtract the mortar joint from the block itself. Thus, the standard block was manufactured to an actual size of 7 5/8 inches by 15 5/8 inches. When laid in a wall with a standard 3/8-inch mortar joint, it occupied a nominal space of exactly 8 by 16 inches. This was a profound conceptual leap. It allowed architects to design buildings on a simple 8-inch grid. A wall opening for a window could be specified as, for example, 32 inches high by 48 inches wide, 4 blocks high by 3 blocks long, and the mason would know it would fit perfectly. It eliminated the need for constant, time-consuming cutting of blocks on site, which reduced labor costs and material waste. The entire construction process became a system of modular coordination, a predictable assembly of interchangeable parts. The 3/8-inch difference, the small void that had been a source of chaos, was now filled with mortar, creating perfect order. The same logic was applied to all dimensions. An 8-inch deep block was actually 7 5/8 inches. A 12-inch block was 11 5/8 inches. A 4-inch block was 3 5/8 inches. Special shapes were also standardized. The corner block had a flat, smooth end for creating clean building corners. The sash block had a groove molded into it to accept a window frame. The lintel block was a U-shaped channel that could be filled with grout and reinforcing steel to span over a door or window opening. Each of these units was designed to fit seamlessly within the 8-inch modular grid. By the end of the war, this system was no longer a recommendation. It was the de facto law of the industry. The post-war era, from the late 1940s through the 1960s, was the golden age of the concrete masonry unit. The GI Bill and the subsequent suburban housing boom created a voracious appetite for building materials. The now standardized CMU was perfectly positioned to meet this demand. It became the default material for the foundations and basement walls of millions of new single-family homes across America. It was also used extensively for the construction of the new infrastructure of suburbia, schools, fire stations, small retail centers, and churches. During this period of explosive growth, the industry's technical and promotional efforts were increasingly led by a new organization, the National Concrete Masonry Association, or NCMA, founded in 1918 but coming into its own in the post-war years. The NCMA worked hand-in-glove with ASTM and other standards bodies to further refine the specifications. They funded extensive research programs at universities and in their own laboratories to better understand the properties of concrete masonry. The work on ASTM C90 continued, with new editions published every few years. The standard became more sophisticated, reflecting a deeper understanding of the material. For example, the classification system was refined. The Grade A and Grade B designations were eventually replaced with Grade N and Grade S. Grade N was specified for general use, including in foundation walls, exterior walls, and other applications where the block might be exposed to weather or moisture. Grade S was limited to use in walls not exposed to the elements, such as interior partitions. The requirements for each grade were spelled out in precise detail in a table within the standard. For Grade N, the minimum average compressive strength for 3 units might be set at 1900 psi, while for Grade S it might be 1500 psi. The maximum water absorption for Grade N would be lower than for Grade S, reflecting its intended use in more demanding environments. Another important classification was introduced, Type 1 and Type 2 units. This addressed the issue of drying shrinkage. As fresh concrete cures and dries, it shrinks slightly. If this shrinkage is not controlled, it can lead to cracking in a finished masonry wall. Research showed that the amount of shrinkage could be limited by controlling the moisture content of the blocks at the time they are delivered to the job site. This led to the creation of Type 1, or moisture-controlled, units. The standard set maximum allowable moisture content levels for Type 1 blocks, which varied based on the average humidity of the region where they would be used. Type 2 units had no such moisture content limitations. An engineer designing a large wall with long, uninterrupted sections, where shrinkage cracks would be visually or structurally problematic, could specify Type 1 units to mitigate this risk. The standards also became more specific about the physical requirements of the blocks. They defined minimum thicknesses for the face shells, the outer walls of the block, and the webs, the internal dividers that create the hollow cores. This was important for ensuring the block's durability, its ability to be handled by masons without breaking, and for providing an adequate surface for the mortar bedding. The configuration of the cores was generally left to the manufacturer, but the minimum material thicknesses were now mandated. To ensure compliance, the standards also detailed the procedures for sampling and testing. For a given lot of blocks delivered to a job site, a building inspector could select a set of units at random for testing by an independent laboratory. The standard would specify how many blocks to select, for example, 5 units for every 10,000 produced, and what to do if a sample failed to meet the requirements. This system of third-party verification provided a crucial layer of quality assurance, giving designers and builders confidence that the materials they were using met the specifications on which their structural calculations were based. Parallel to the development of standards for the blocks themselves, a similar effort was underway to standardize the other components of the masonry wall system. ASTM developed specifications for masonry mortar, ASTM C270, which defined different types of mortar, type M, S, N, and O, with varying compressive strengths and bonding properties, allowing designers to select the appropriate mortar for a given application. They also created standards for the grout, ASTM C476, used to fill the cores of blocks to increase a wall's strength or to anchor reinforcing steel. This holistic, system-based approach ensured that every element of a concrete masonry wall was a known quantity, with predictable and reliable performance characteristics. By the 1970s, the world of concrete masonry was one of remarkable order and predictability, a stark contrast to the chaos of its early years. An architect in California could design a building using standard 8x8 by 16 CMUs, and a contractor could build it using blocks manufactured in a local plant, confident that they would meet the same dimensional and quality standards as blocks made anywhere else in the country. This interchangeability was the silent engine of efficiency that allowed for the rapid and economical construction of the post-war American landscape. However, new challenges in the 1970s and 1980s would force the industry and its standards to evolve once again. The oil crises of 1973 and 1979 brought the issue of energy conservation to the forefront of national consciousness. Building codes began to mandate higher levels of thermal insulation to reduce the energy consumed by heating and cooling. The traditional concrete block, made with dense sand and gravel aggregate, was a durable and structurally efficient material, but it was not a particularly good insulator. Heat could travel relatively easily through the solid webs and face shells of the block, a phenomenon known as thermal bridging. This new pressure spurred a wave of innovation in the industry, aimed at improving the thermal performance of CMUs. One approach was to change the aggregate used to make the block. Instead of dense, normal-weight aggregates like sand and gravel, producers began to use various lightweight aggregates. These were materials like expanded shale, clay, or slate, which were heated in a kiln until they bloated, creating a porous, lightweight structure full of tiny air pockets. Other lightweight aggregates included pumice, a natural volcanic rock, or industrial byproducts like expanded slag. Blocks made with these aggregates were significantly lighter than normal weight units, making them easier for masons to handle, and their porous structure gave them a much higher thermal resistance, or R value. ASTM C90 already included provisions for lightweight blocks, categorizing units based on their oven-dry density. But the increasing focus on energy performance led to more detailed research and classification in this area. Another strategy was to add insulation directly into the cores of the blocks. This could be done on the job site by pouring loose-fill insulation, such as perlite or vermiculite, into the block cores as the wall was being built. A more effective method developed by manufacturers was to pre-insulate the blocks at the plant by inserting custom-molded polystyrene or polyisocyanurate foam inserts into the cores. These inserts were designed to fit snugly, minimizing air gaps and significantly boosting the overall R value of the wall system. These innovations required new testing methods and new ways of classifying performance. The old standards focused almost exclusively on structure and durability. Now, thermal properties had to be measured and certified. ASTM developed standard test methods, such as ASTM C177, the guarded hot plate apparatus, to precisely measure the thermal conductivity of materials. Manufacturers could use data from these tests to publish the R values of their various wall assemblies, allowing architects and engineers to design buildings that complied with the new, more stringent energy codes. Alongside energy performance, another critical property that received increased attention was fire resistance. Concrete masonry has always been known as a non-combustible material with excellent fire resistance, but a more systematic way of quantifying this property was needed for building codes. This effort was led by organizations like Underwriters Laboratories, or UL, and by ASTM through its Committee E5 on fire standards. The fire resistance of a wall assembly is determined by subjecting it to a standard fire test, such as ASTM E119. In this test, a full-scale sample of the wall is built and placed in a large furnace. The temperature inside the furnace is raised according to a specific time temperature curve, simulating the conditions of a building fire. The wall is evaluated on several criteria. It must not collapse under its own weight or any applied load. It must prevent the passage of flames or hot gases. And the temperature on the unexposed side of the wall must not rise above a certain limit, typically 250 degrees Fahrenheit, above the ambient temperature. The fire resistance rating is the length of time the wall can satisfy all these criteria, typically expressed in hours, such as a 1-hour, 2-hour, or 4-hour rating. Extensive testing revealed that the fire resistance of a CMU wall depended on several factors. The most important was its equivalent solid thickness. This is a calculated value that represents the thickness of a solid block made from the same amount of concrete. For example, a hollow 8-inch block might have an equivalent solid thickness of 4.5 inches. The greater the equivalent thickness, the longer it takes for heat to travel through the wall, and thus the higher the fire resistance rating. The type of aggregate also played a crucial role. Lightweight aggregates, particularly those with low thermal conductivity, like pumice or expanded shale, performed significantly better in fire tests than normal weight aggregates. A wall made of 8-inch lightweight blocks might achieve a 3-hour rating, while a wall of 8-inch normal weight blocks might only achieve a 2-hour rating. The NCMA and other organizations compiled this vast amount of test data into tables and design aids, allowing architects to easily determine the fire resistance rating of a given wall design without having to conduct a new test for every project. This system of pre-calculated, standardized fire ratings provided the same kind of predictability and reliability for fire safety that dimensional standards had provided for construction efficiency. By 1980, the 60-year journey from chaos to order was largely complete. The concrete masonry unit had been transformed from an inconsistent, localized craft product into a highly engineered, precisely manufactured component of a sophisticated building system. Its dimensions were standardized to a fraction of an inch, enabling seamless modular coordination. Its structural properties were defined by a series of consensus-based standards, allowing for reliable and efficient engineering design. Its performance characteristics, from thermal resistance to fire ratings, were quantified through rigorous testing, enabling designers to meet the complex demands of modern building codes. The story of the standardization of the concrete block is not a dramatic one. It has no famous heroes, no epic battles. It is a story of quiet, patient, and often tedious work conducted in laboratories and committee meetings. It is a history written in the fine print of technical specifications, in tables of compressive strength data, and in the meticulous drawings of testing apparatus. Yet, the impact of this work is monumental. It is embedded in the foundations of our homes, the walls of our workplaces, and the very fabric of the modern city. The unassuming, grey block, with its precisely calculated dimensions and its carefully specified properties, is a testament to the power of collaboration and the relentless, methodical pursuit of order. It stands, quite literally, as the bedrock upon which much of our world is built. Its silent, standardized strength, a quiet legacy of a 6-decade effort to build a better, more predictable and more reliable world, one block at a time. And in the quiet uniformity of those blocks, in the perfect alignment of their mortar joints, we can find a certain calm, a certain peace, knowing that even the most mundane objects around us are the products of immense, unseen effort, designed to bring a small measure of order to a complex world.